Bismillahirrahmanirrahim. Assalamu alaikum dear students, welcome back in lecture 14. Students, we do not complete basically lecture number 13 and we will discuss about further, okay, about lecture 13 in lecture 14, okay. So here we have basically we are checking this development length. Remember the formula which I am using here. If you go to the Nielsen book and you just found out this table in chapter 6 barn anchorage and development length. Here you see the formula which is this one. Now this formula is available in ACI new version. Basically the formula which I am using basically in my Excel sheet is basically present as well as in ACI code, but this is a little bit different formula used in old versions. This is basically 0.02 times of FC prime, basically FY, sorry. Let me check it whether it is FY. So here we have this is FY, okay, and then we have to, this is diameter of the bar which you are using, dB. This is diameter of the bar which you are going to be using, and the diameter of the bar is 0.5. so that why to basically we first of all need to find out the diameter of the bar. Let's say I find out the diameter of the bar here. So this is my area. So what I need, how to find the diameter of the bar? This is my area. So this area times 4 pi d square by 4, okay, and this is divided by phi value, that is 3.14, and bracket close, and we have to take square root. So square root will be 0.5. Clear? So this is the diameter of the number 4 bar. If you want to apply this for all those formulas, just check this, okay, and once you check it, then okay, and then drag this formula. This will be applicable now for all the, you see the diameter of all these bars. Now if you need to remove all the bars, sorry, we need number 4, so you can do this, okay, and this we need this one, okay. Now just merge it and remove this one. Clear? This is this one is background color, so let me change it, let me no fill, and here you see dB. Clear? Or you can write this dB, okay. Now we change this formula, okay. So here we have this one will be now my this one. Clear? And square root of FC prime, okay, this is square root of FC prime, so this is 9 inch. Clear? And now this one is 0.0003 times, and this formula basically you see in Nielsen book, 0.0003 FY into dB. Clear? So this is FY, this is okay, and this is dB. Now I have to search dB, this one, and okay, so this is 9, and you round this, okay, and 8 is the minimum. So you have to select the maximum value from these values, okay. So here we have equal, and using the maximum formula, okay, this one we need to find out the maximum value from this one, yes. So that's why I'm written the things, because these are self-calculated values, okay. So the available LD is 8 inch, and this is calculated by the sheet, okay. And remember, this is total depth, that is I think so 1 feet. Let me check it. This is 1 feet. Yes, this is 1 feet. And next is, this is 3 inch clear cover, okay. And here we have basically 1 bar, not 2 bar, because if you watch this video, you see in this video that the bar is basically parallel to the downward bars, or you see here, okay, the bar is, this hook is basically parallel to these bars. So that why this hook is basically placed on this bar, okay. But here you see for this bar, the bar is just above above the bottom and top bars. So that why for this hook you have to use 2, but for this you have to use 1. So that why it depends upon you. Now you are using 2 or 1. I think so 2 will be more conservative. Okay, so use 2 and check this one. This is basically diameter of the bar, dB. Okay, this is diameter of the bar, 2 times diameter of the bar. Okay, and this is 2 times diameter of the bar, because here we are using 2 bars. Okay, and the diameter of the bar is this one. Clear? So here the available clad cover is basically this one, 8 inches, and already we calculated 8 inches. If you use 1 bar, then it will be 8.5 inches, and this is clear from this video. Okay, you see, for this bar this D is basically 8.5, but for this hook this is 8 inch. Remember, this is the difference. And the concrete which is placed here, let me show you the development length here, LDC. Okay, here we have. Okay, so the development length is basically calculated from the face of this concrete to that hook top surface. Clear? So you must understand this. And LD will be provided to this is important, that our calculated LD is now 9 and this is 8. So we need hook. We have, because 1 inch difference is not almost greater difference, so you just provide that hook, it will work. Okay, and if it is larger depth, then you have to increase the depth of your footing, thickness of your footing. Okay, and this ends of the design and analysis, and basically here the final calculations are okay. This is 7 feet and this is 1 by 1 column, and these are the dowels, and here finally number 4 at the rate of 6.5 inch both way. Okay, remember this is end up. Now I am explaining very interesting things that are basically my tributary area calculations. As we did tributary area calculations, I think so, in lecture number 7 at roundabout. Okay, with very clear, very deep detail. Okay, and if this one. Okay, this is for non-uniform panels, and this one is for uniform panels, square panels. Okay, we did these calculations and we find out basically 1.04. Now I will show you an Excel sheet, and I will provide this sheet in my description. Okay, link I will be provided. Here you see that let's say I am calculating the loading to the beam in panel C. So in panel C, dimensions is 19 feet, and here my slab thickness 5.5. It will be automatically calculated. My SDL, service dead load, is 38. Remember, this is right here. I will show you in the beginning of this lecture that we calculated our service load just at these two values. This is your SDL, and this one will give you the self weight of the slab. Okay, so you don't need to be confused. Okay, in these values, this is my 38, 40 is my live load, and this is my factor load. Remember, I am using 1.4 and 1.7. if you are using 1.6, so change this 1.6 and 1.2. Clear? And now this is my dimensions, these are my tributary areas, and you see our tributary area is 89. Okay, so this is okay, 1.03 or 1.04 close. Okay, so these are my loading which is basically acting on my beam. You are here, you see. Okay, this is the way. If for example this is a non-uniform panels, okay, like in this case, so it will automatically calculate things. Okay, automatically calculate things. For example, if I want to show you from Hebler book, this is a Hebler book, and here we have I think so this in this chapter. For example, let me show you here this one. So here you see this is 10 feet shorter, and this is larger, that is 15 feet. Clear? So let me show you. This is smaller dimension is 10 and larger dimension is 10 feet, 15 feet, sorry. So you see automatically they calculate 500 and roundabout. So this will be the load on the smaller beam, and this will be the load on the larger beam. So this is this, I will provide this sheet as well. And the last one, that is this Excel sheet. Okay, So this is also important, okay, and I want to explain this, okay. Remember that once you this is, let's say I will do calculation for panel C, and panel C is 19 and this longer span will be 19 point, let's say 001, because for same dimension it do not work. Thickness is 6 inches. Remember that they are using 5, we are using 5.5 inches, and this is my 38, but let's say we are using conservative to, okay, because here they are using 5, so we use a little bit lower value of HDL, superimposed load, that is 38 in our case, but let's say we are using this one, and 4 and 60. Clear? Now as panel C all edges are continuous, so here we have all edges are continuous. The sheet gave you number 3 to the rate of 10, number 3 to the rate of 7.5. You see there is larger, the negative movement is larger, okay, the negative movement is larger, and the panel is square, so that you see this movement equals to this movement and this movement equals to this movement. This is also very important. And you see that in square panel, basically this is critical analysis, that in square panel basically the loading distribution on all beams are same, but when you are dealing with a rectangular beam, so you have to watch basically the longer span beam, because to what span maximum and minimum loads are transferring, okay, to mostly to the larger side of the beam maximum load is transferring, okay. So this is the way, okay. Now if I see our calculations and you compare the things, okay, here I have this one. So in panel C basically you see this is our moments, okay, and these are our load coefficients, and that are basically taken from the tables. Clear? And I already explained this. Now this is 42.6 kif inch. Clear? And we are using number 4. Basically if you are using number 3 bar, then the spacing will be minimized, coming to 7.7 inches or 7.5 inches around about, okay. Please do that calculation. Now my movement is 42.6. if I divide this movement on my calculator, 42.6 divided by 12, I got basically 3.55, and my Excel sheet basically giving me 3.61 almost, and 3.55 almost are same. So if I want to show the drawing, so let me show you the drawing. This is the drawing, and this is the arrangement which is provided for the reinforcement. You see this is the top reinforcement or the negative reinforcement which is provided in the top portion, and here if I show you the detailing of this, okay, so let me show you the detailing of this one, okay. Let me rotate things. No, it is rotate to right, yes, this one. Now you see in panel C basically, so these are the top reinforcement. Remember, these are the top reinforcement, and Excel sheet basically giving me that this reinforcement will be number 3 to the rate of 7.5 in center to center up to a distance of L by 3, okay, but providing in the top, and you have to continue this to the other side as well. And this is 19 feet and this is 19 feet, okay, and here the same thing and here the same thing. And remember, this arrow shows that this will be in this direction and this will be in that direction. Clear? And remember one thing, you see the positive reinforcement number 3 at the rate of 10 inches. This is also important, that when all the edges of the beam of this panel is supported or continuous, so you see there will be lesser amount of movement basically present in the middle, in the positive movement region, but larger movement on the supports. So that why we have to basically see this reinforcement, and this reinforcement is critical, not the middle one, okay, not the middle one. Basically the positive reinforcement is critical, okay, the negative reinforcement is critical. Clear? This is very important, and I will explain this, okay, and in my previous lectures. And what are the other things, okay, and for example, if I design this panel, so let's see, we see the effect. Okay, we see the effect. In my panel A, my short span is 18.87, clear, and my longer span is round about 18.9375. okay, so here I have basically in panel, if I assume the panel that is, let's say I am designing this panel, clear. So you see this edge is continuous and all the other edges are discontinuous. So let's see, if we discontinued edges, like this one is continuous and this one is discontinuous. Okay, this one is discontinuous. Now you see the maximum moment here at the continuous edge. So this is a critical analysis. Remember, whenever you are working on a site, okay, whenever you are working on a site, so this is very important for you, that there, if you are, for example, you are a site engineer and you face such kind of situation that there is wall 3 sides but there is beam, and they are providing tough reinforcement and its spacing is minimum than the other reinforcement spacing. So you have to point out this okay, and you have to report the structural engineer, okay, because this is how I want to show you as a designer, that if you are working as a site engineer, the bars which you are providing here, it must be close as compared to these reinforcement which you are providing here, as well as in positive region and spacing, because this is critical section right now. And similarly here you see these are the critical region in panel C, because these negative reinforcement is now my critical. Okay, this is critical, this is very critical. And you see the effect of discontinuity as compared with the continuous. Okay, here all edges are discontinuous, so you see there the movement is larger, the maximum one, as compared to all panels. And here you see all the edges are supported, all the edges are continuous, so there will be a little bit effect on the positive, but here is the most larger effect. So that's why the spacing should be minimum in the negative movement region, and should be minimum in the positive movement region. This is the critical analysis. If you are working on a site engineer, you must have to report these things, clear. And if the structure, because most of the time if you find such drawings, basically they are designed by non-professionals, you can say they first time, they don't understand these things. And nowadays you see most of the people do designing, but they don't know about the basics of designing. Okay, they just copy paste things. So if you are a site engineer and you are working, so you have to point out these things, and I think so you will got impression in your company as well if you are finding out such kind of errors. Okay, so that's the key purpose of this lecture, okay, that I want to show you this critical analysis. Okay, so here you see that here we have the maximum 4.5 inch center to center, almost you compared with others 10, you see 10 and 9.5. okay, so this is the positive region, because this is the shorter span, longer span, sorry, and this is my shorter span, and here you see 10. So this reinforcement is very critical. I think so this ends up, you got a lot of information regarding these topics, and in coming lecture inshallah I try my best to cover the design of staircases. Okay,